My presentation is on the science of remote sensing. This image below is a satellite image of the Congo River Delta. There's two main types of remote sensing. There's active and passive remote sensing. Active remote sensing is typically done through radar, LiDAR, and sonar, and it's emitting radiation pulses onto the Earth's surface and recording the time it takes to bounce back to the sensor. This is usually done by airplane, or more recently, they figured out ways to conduct LiDAR by drone. Passive satellite imagery mainly consists of Landsat imagery, and it's using cameras to essentially photograph the Earth's surface and also take in the visible and invisible light spectrum. So it's conducted using satellites that orbit the Earth. As I mentioned earlier, LiDAR is usually conducted through planes. The plane emits a radiation pulse onto the ground and records the time it takes to bounce back to the sensor, and that gives it the elevation of the area. One thing with LiDAR is that it does not typically include vegetation, but it does include buildings. However, one issue with LiDAR is it can have errors, and one major issue with it that happens a lot is backscattering. So this happens when the radiation pulse hits the ground and bounces back on another object before hitting the sensor again. So this can give it a false idea of what the elevation is like because it hit more than one object. So it can be either recorded as higher or lower elevation than it actually is. Sonar is used to map the ocean floor. Instead of using radiation pulses, it uses sound pulses, and it records the amount of time it takes to hit the sensor after hitting the ocean floor. And this gives it an idea of what the ocean floor looks like. Sonar is usually active sensing, but it can be passive remote sensing. This is pretty rare, though. It's only really used with military vessels that want to detect incoming objects. So sonar is mainly active remote sensing, especially for the purposes of GIS, and it's typically conducted through NOAA, which is the National Oceanic and Atmospheric Administration. And one more thing, similar with LiDAR, sonar is not going to capture any vegetation, not very much vegetation that's on the ocean floor. It's going to just record the elevation, nothing that's going to give us an idea of what it actually looks like other than the elevation. Landsat imagery is the main source of passive remote sensing. It's funded by NASA and USGS, which is the U.S. Geologic Survey. So this over here is a screenshot of Google Earth imagery. This is what it looks like. It essentially records the reflections of the electromagnetic spectrum from the surface to the sensor, which I'll talk about in the next slide a little bit. The Landsat satellites are the satellites that orbit the Earth that give us our Landsat imagery. So as you can see, there's been about 8 Landsat satellites. The current one that we're using is Landsat 8. It first launched on February 11th, 2013. So that's the main one that we use. It also looks like the one launched in 1999, Landsat 7, is used as well. So satellite imagery records the electromagnetic waves that hit the sensor. This is the electromagnetic spectrum right here. The sensors on the satellites record visible and invisible waves. So this is the entire spectrum, and the only part that we're able to see as humans is the visible light spectrum. The gamma rays right here are the shortest waves, the radio waves are the longest, and the length of the wave tells us how long it takes for the waves to travel. So gamma rays are very, very quick, and radio waves are much slower. Some colors in the visible light range are easier to see. For example, green has one of the highest reflection rates in the visible light spectrum because it has the highest reflection rate. Incident radiation is the combination of absorbed, reflected, and transmitted radiation. The only type of radiation that satellites use is reflected radiation. So essentially, the sun emits radiation onto the ground, bounces back up, and the satellite records that reflected radiation. It doesn't just, so it's multispectral, meaning it's not just taking an image of the ground, but it's also collecting data on the visible and invisible light spectrum, which becomes very useful when you're analyzing the data. So ERDOS is an application that can be used for analyzing imagery. For satellite imagery, it separates the images by pixels and classifies them, which makes it easier to view. So spectral classification is what this is called. You can see in this image right here that the vegetated areas are red and the river, and it looks like even the soil is blue, which is obviously not how the Earth looks naturally, but it was edited using ERDOS, so it's easier to differentiate between the vegetated land and the river. Another thing that ERDOS can do for satellite imagery is it can also pan sharpen images given a panchromatic band, so it can make the images a lot sharper and more high resolution, which is very useful. Some areas of, if you look on Google Earth, you can tell that some areas are not as high resolution as others, so this is especially useful for that. ERDOS can also be used for analyzing LiDAR data. Unlike ArcGIS Pro, ERDOS can view LiDAR data in 3D, and it actually allows you to pan across the entire portion of the data. It allows you to view intensity, classification, elevation, and various returns. It can split elevation into color ranges. So as you can see, the high elevations are red, then it's yellow, green, light blue, and if you look on the very bottom left corner over here, the lowest elevation is dark blue. So it can split it into color ranges, and that makes it a lot easier to view. It also can generate slope, aspect, contour, and view sheds. This is also similar to ArcGIS Pro. You can use the toolbox to calculate slope and aspect, so this is similar to ArcGIS Pro in that sense. The system also has tools to remove void areas, extract valleys and ridges, and drape images in a virtual GIS viewer. ERDOS also has tools to essentially slice elevation data into a certain number of bins, which makes it easier to analyze. And it also has tools to visualize Z values or reflectance spectrum of a certain area. Lastly, ERDOS can be used to analyze radar data. I didn't talk much about radar data in this presentation, but the main types of radar data are Sentinel-1, RadarSat, and TerraSAR. The radar toolbox in ERDOS can help for real and synthetic aperture radar. Synthetic aperture radar is conducted using a much smaller antenna than is needed, but it mimics the size of a large antenna. So that's what synthetic aperture radar is. And so this radar toolbox can be used to extract DEM, texture, and polarimetric classifications. Essentially, what this means is that it can actually manipulate radar data. So you don't need to convert the radar files at all. You just drag it into ERDOS and you can go from there. You don't need to even convert it. And these are my references.